Hello everyone, so let's continue our discussion about partial fraction decomposition. So what did we learn in the previous video? Well, in the previous video we learned how to write a partial fraction decomposition of a rational function where in the denominator you have distinct linear factors. So let's start with an example. Okay, so x plus 5 over x square plus 9x plus 20. What you do first is you make sure you shall we do the second problem? So we factor the denominator as much as possible. So if we factor x square minus 5x minus 14, you would get x minus 7 and x plus 2. Now for each factor in the denominator, you will have a corresponding fraction in the decomposition, right? So for x minus 7, it's a over x minus 7. For x plus 2, it's b over x plus 2. So a and b are constants, just numbers. Why do you choose a and b? Why do you choose constants? Because the numerator should have a polynomial 1 degree less than the denominator. So in the denominator, we have a linear polynomial, right? x minus 7, x to the power 1. So degree 1, 1 minus 1 is 0. So 0 degree polynomial means it's a constant. So that's distinct linear factor case. Super easy. Now how about if you have repeated factors? So let's write down a couple of examples. So x plus 5 over x square plus 2x plus 1. So the very first thing you do is again you factor the denominator as much as possible. So if you factor, you get x plus 1 square. Now let me take a general case like x plus 9, and we have like ax plus b. A and b are numbers sum. So what do we do? Alright, so we have repeated factor here. We have a repeated factor. X plus 1 is repeated twice. So that is the meaning of these two. Now let's understand a very important thing here. So let's take that factor, x plus 1 square. Now this 2 here, right here, it's called multiplicity. Okay, multiplicity. Now what is multiplicity? Multiplicity means how many times your factor is repeated. So x plus 1 is repeated 2 times, so multiplicity is 2. So the way you read this whole expression is your linear factor is repeated twice, or degree 1 factor is repeated twice. Okay, think this as repeated. Okay, I'm just lazy. So multiplicity is 2, degree is 1. Now there's a very misconception that most of you think that this is degree 2 also, because actually what is x plus 1 square? X plus 1 square is actually x square plus 2x plus 1. Of course, if you expand this, right? So of course this is a degree 2 polynomial. Why do you call it a degree 1 polynomial? Well, it's just the way we read this is different from what we have here. So my point is, in your mind, don't think these repeated factors as expansions in your mind. Don't expand x plus 1 square and think it like x square plus 2x plus 1. No, the way you should think about a repeated factor is that, okay, I have a degree 1 factor. Inside the parentheses, I have a degree 1 factor, x plus 1, x to the power 1. It is repeated twice. This is multiplicity. Okay, so that is how you should read it. Okay, hopefully that's clear. Well, we'll see examples. So it's going to come up later. It's super important, the difference. All right, now, well, how do we write the decomposition? We didn't discuss that yet. Okay, so let me erase this stuff. So here's the thing, the way you write the decomposition is, okay, so let's take this general case. Take the factor. So we know ax plus b is repeated n times. Multiplicity is n. Okay, now what you do is you count up to n. Okay, count up to n means, so 1, 2, 3, write all the numbers until n. So n is the last number, the number before n is n minus 1. Now what you do is you take the power of ax plus b for each of these numbers. So like ax plus b to the power 1, then comma ax plus b to the power 2 for this 2. Okay, and then ax plus b to the 3, and then blah 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 blah, that goes on, and ax plus b to the n minus 1. You take the power until you reach this number n. Okay, so that is why I said count up to n. Okay, so for example, in this case, x plus 1 is the factor. It is repeated twice, so count up to 2. So 1, 2. Well, that was easy, right? You stop at that number. So you have x plus 1 to the power 1 and you have x plus 1 to the power 2. Okay, so you take the power of each power of that factor for each of the number in your count. Okay, now you get so many versions of this same factor with different powers. Now for each of these power, you will have a corresponding fraction in the decomposition. Okay, so yeah, this is really messy, right? So what you have here is the decomposition of this fraction right here is a over x plus 1, that's for 1, power 1, plus capital B over x plus 1 square, that's for 2. Okay, that's the decomposition. So the decomposition for this fraction will be like this: ax plus b1, capital A over ax plus b, plus capital B over ax plus b square, okay, plus c over ax plus b cube. So you write a fraction for each of this power for that same factor until you reach that multiplicity n. Okay, all right, so let's see more examples, then it will make sense more. All right, so let's look at this one, this problem. So you have to decompose this: x plus 5 over x cube plus 3x square plus 3x plus 1. So let's factor this, factor the denominator. So if you factor the denominator, you will get x plus 1 cube. Okay, don't worry about how I factor it, just focus on how to write the decomposition. All right, so now how do you read it? X plus 1 is repeated 3 times. Multiplicity is 3. Degree 1 factor repeated 3 times. Now count up to 3. So 1, 2, 3. Okay, so the decomposition is a over x plus 1 to the power 1 plus capital B over x plus 1 to the power 2. And guess what is the third one? C over x plus 1 to the power 3. How about if this 3 was like, come on, okay, so if this 3 was like 5, then what would be the decomposition? 5 here. So then the decomposition is a over x plus 1, b over x plus 1 square, c over x plus 1 cube. What is the next one? D over x plus 1 to the 4. And what is the final one? Yes, you're right, e over x plus 1 to the 5. Okay, so I hope you get what I mean. Okay, so you count up to that number multiplicity and you represent each number in that count as a power of the factor you have in the denominator. Okay, all right, so how about a mixed case scenario? So something like this. So we have 1 over x plus 7 and x square plus 4x plus 4. So let's factor this. You have to factor as much as possible. So x plus 7, and here if you factor x square plus 4x plus 4, you get x plus 2 square. Now look at this fraction. We have distinct factors, linear, but x plus 2 is repeated. So how do you solve this problem? Well, x plus 7 is not repeated. It's just a simple distinct linear factor. So how do you represent them? Just a over x plus 7, right? Like we learned in the previous video. All right, then how do you deal with x plus 2 square? Now the multiplicity is 2, count up to 2, 1, 2. So for capital B over x plus 2, that's for 1, and capital C over x plus 2 square. Okay, so that's how you deal with a mix of distinct linear and repeated factors. So okay, all right, so I want to answer one last question. Now here's why I discussed the difference between multiplicity and degree at the beginning of this video, like the way we read it. So the way we read it, x plus 2 square is the linear factor, degree 1 factor x plus 2 repeated twice. Okay, so it's degree 1. Do not think this as x square plus 4x plus 4 and think this as degree 2. Okay, don't read it like that. Now why did I say that? Remember I said we choose our numerator in the decomposition to be a 1 degree less than what you have in the denominator. Now one could argue, well, hang on a second, this is degree 2, x plus 2 square is x square plus 4x plus 4. So then this is degree 2 2 minus 1 is 1. So this should be a degree 1 polynomial. It shouldn't be a constant. Okay, so this c should be like cx plus e. So this is a degree 1 representation of a degree 1 polynomial. So why do we still have constant here then? Why don't we write this? The reason is the way we read it. The way we read a repeated factor is actually, this is a degree 1 factor repeated twice. Okay, it's not a degree 2 polynomial. The way we read it is different. So I want you to wrap your head around it. X plus 2 is a linear factor. It's repeated twice. It's not x square plus 4x plus 4. I know it is x square plus 4x plus 4, but forget about it. Okay, so it's a linear factor repeated twice. So that is why, so it's still degree 1. Okay, degree 1 factor repeated twice. So that is why still we have a constant, because degree 1 minus 1 is 0, degree 0 polynomial is a constant. Okay, all right, so shall we wrap this video with one example? X plus 8, x plus 1, how about x plus 6 to the power 4? How do you write the decomposition? So x plus 1 is a distinct linear factor, so it's distinct from x plus 6, so a of x plus 1. Okay, and x plus 6 to the 4 is b over x plus 6, count up to 4, 1 2 3 4, c over x plus 6 square, d over x plus 6 cube, and e over x plus 6 4, count up to 4. Okay, each power is represented. So this is the decomposition. So I know it's slow. All right, so in the next video now we learn how about if we have repeated factors but they are not linear. Okay, so it's something like x square plus 1 square. Now this is degree 2 factor repeated twice, because what you have inside the parenthesis now you have 2, so they are not linear anymore. How do we deal with this? Okay, so let's discuss that in the next video. Okay, all right, thank you very much. Bye bye.